Hi again, this is the second video for lesson 5-1. At the end of the last video, I think I said this would be video 5-2, which of course it is not, because that means we would be moving ahead to the next lesson. Sorry about that. So this is just the second video for 5-1. So what I want us to look at now is a little bit of background understanding on why this works out the way that it does. This is below the theorem and the converse that we just did. I'm looking at this proof for perpendicular bisector theorem, and we're not exactly going to walk through the proof, but I do want to just explain a little bit to you. If you look at the diagram in the proof or beside the proof, I'd like for you to see a few things. First of all, we have two triangles. They are divided by this perpendicular bisector. We know for a fact that it is a perpendicular bisector because it's perpendicular and because it bisects this segment into two equal parts. So building on that, if you were to think about our triangle theorems that we've been working on and that you actually just took a test on, we have two congruent sides and two congruent angles because we have this side congruent to this side and this angle congruent to the one right next to it. We have one more thing. If you pause to try to find it for just a second, hopefully you will see that we also know that xy is congruent to xy based on the reflexive property. That gives us another side. So we have now proven that this triangle is congruent to this triangle based on side, angle, side. So what I want you to see there is that we can then go on to say that this side is congruent to this side based on corresponding parts of congruent triangles are congruent. Corresponding parts, this corresponds to this, of triangles that have already been proven congruent, which we did, are congruent. So using that, I can say AX is congruent to BX. And in doing so, I'm really just proving what the perpendicular bisector theorem says. It says if a point is on the perpendicular bisector, which is L in this case, then it is going to be equidistant from the endpoints of that segment. Well, we just proved that that's true because we proved that this is going to be equidistant with this based on corresponding parts of already proven congruent triangles are congruent. So I just wanted y'all to see that little bit of information and kind of how we can know certainly that this works. And then I want to expose you to one more thing. We're going to be exposed to this word right here, locus. So let's look up just a little bit at reading math. The word locus comes from the Latin word for location. The plural of locus is, I think you actually say it loci. Oh, yeah, it tells us that below, which is pronounced loci. Okay, and we come over here. A locus is a set of points that satisfies a given condition. The perpendicular bisector of a segment can be defined as the locus of points in a plane that are equidistant from the endpoints of the segment. So again, a locus, another word for locus, or the definition of locus, is a set of points. A locus is a set of points that satisfies a given condition. In our case, the perpendicular bisector, let's look at the picture right here, is a segment that can be defined as a locus of points, so a whole set of points that are equidistant from the endpoints of the segment. So it's not only X that's equidistant from A and B, but we could pick any other point above X or below X, and each of those points, each of those infinite number of points that make up that line would be equidistant from A and from B because of the perpendicular bisector theorem. All right, we will stop there, and in the third video, we will pick up at the top of page 301.